Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the Electrical Engineering channel. In this lecture, I will explain how to evaluate the matrix exponential. So, matrix exponential means if we have a matrix as the power of the exponential function, right? For example, e raised to power a, e raised to power at, and if a is a matrix, then this expression will be called as matrix exponential. And this matrix exponential actually originates from the solution of a system of differential equations. So for reaching the derivation of the matrix exponential, let's first consider the simplest case of a linear differential equation. So this is the simplest first order differential equation, and this is a single linear differential equation. It is not a system of differential equations. And in this case, we have only one ODE, which is du over dt is equal to au. So let's try to solve this differential equation. And after the solution of this ODE, we will reach the result for this system of linear differential equations and this matrix exponential. So du by dt is equal to au, and we can combine like terms on one side. For example, we can take all terms containing u at the left hand side, and all other terms can be taken to the right hand side. So du over u is equal to a times dt. So integrating both sides, we will have 1 by u du integration is equal to a dt integration, and it will be equal to natural log of u, and the integration of this expression will be a t plus c. After taking the anti-log, we will have u equal to exponent power at plus c, and e raised to power at plus c can be written as e raised to power at multiplied by e raised to power c. Now e raised to power c is another constant because the c was the constant of integration. Now e raised to power c is another constant. Let's denote it with k. So u will become k times e raised to power at. So now we can apply initial conditions to evaluate the value of this constant of integration k. And after applying the initial conditions, we will have u at 0 is equal to k e raised to power 0. So e raised to power 0 will be equal to 1, and k will be equal to u at 0. So let's apply k equal to u of 0 in this equation. We will have u is equal to u0 e raised to power at. So this is the solution of this first order ODE. Now suppose we have a system of linear differential equations, then those system of linear differential equation can be written in the matrix form as this. So here we have actually two differential equations. First differential equation is du1 over dt equal to minus 2u1 plus u2, and second differential equation is du2 over dt equal to u1 minus 2u2. So these two differential equations can be written in the matrix form, and the column vector of u du1 over dt and du2 over dt is written as du by dt. Here we had u1 and u2, which are represented by this u column vector, and here we will have the A matrix. So since the solution of this differential equation is u equal to u naught e raised to power at, and at was the scalar, for this differential equation, the solution will be equal to u equal to e raised to power capital At u0, right? Because here we had small a, and here we have capital A, and this capital A is equal to the matrix. So the solution of this differential equation is u equal to e raised to power capital At multiplied by u0. And e raised to power At is called matrix exponential. And if we have a matrix as the power of the exponential function, then the result will also be a matrix which has the same order as this matrix A, right? So let's learn how to solve this matrix exponential. From the conventional method, which we discussed in our previous lectures of solution of higher order ordinary differential equations using eigenvalues and eigenvector method. We learned that the general solution of any system of linear differential equations can be evaluated based on the nature of the eigenvalues. So here we have this matrix A. The eigenvalues of this matrix A are -1 and -3, and the two eigenvectors are 1, 1, and 1 minus 1. These are the two eigenvectors of A, and these are the two eigenvalues of A. So the general solution based on the types of eigenvalues can be written as ut equal to c1 e raised to power lambda 1 tx1 plus c2 e raised to power lambda 2 tx2. And we can apply initial conditions to evaluate the values of these two constants c1 and c2. So let's substitute t equal to 0. So we will have u0 equal to c1 x1 plus c2 x2. So this is our u0, and this can be written as uh, uh, x1 is equal to 1 1, x2 equal to 1 minus 1, and c1 c2 can be written as the two elements of a column vector. So 1 1 1 minus 1 into c1 c2. This is our S matrix, matrix of eigenvectors, and this is our C matrix, which is c1 c2. So from here, C can be written as S inverse U0, right? This is U0 equal to SC. So C will be equal to S inverse U0. So we can substitute this value of C in this equation, which is equation 2. And in this equation 2, we have actually represented this solution in the matrix form. So this is our C1, this is our C2. They are written in the column vector, and e raised to power lambda 1 t, e raised to power lambda 2 t, they are written as the diagonal entries of this matrix, right? And x1 and x2 are written as this S matrix. So if we multiply these three matrices at the end, we will get this equation. So this equation and this matrix form, they are similar. So we can substitute this C equal to S inverse U0 in this equation. So we will have ut equal to 1 1 1 minus 1. This is e raised to power minus t, e raised to power minus 3t, and this is our S inverse and U0. So this is the solution, and this can be written as ut equal to S e raised to power lambda t, right? Because -1 and -3 are our eigenvalues, so e raised to power lambda t. This is also a matrix, and here we will have S inverse, and this is U0. So lambda is a diagonal matrix with eigenvalues at the diagonal, and from equation uh, this equation, we know that the solution is u equal to e raised to power a t u0, and here we have ut equal to s e raised to power lambda t s inverse u0. So we can compare these two equations. So by the comparison, we can conclude that this e raised to power at is equal to s e raised to power lambda t s inverse, right? So e raised to power at is equal to s e raised to power lambda t s inverse. So this is how we can evaluate the matrix exponential. So we must know the matrix of eigenvectors of A, which is S matrix. Here we will have the inverse of this S matrix, and in between we will have e raised to power lambda t. So if this is a 2 by 2 matrix, e raised to power lambda t will also be a 2 by 2 diagonal matrix. And the diagonal entries will have e raised to power lambda 1 t and e raised to power lambda 2 t. Lambda 1 t and lambda 2 t are the two eigenvalues. So that is all about our today's lecture, and that lecture was also very important because we have learned how to evaluate the matrix exponential, and by adopting this method, we can calculate the matrix exponential by using this simplified expression. So for watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.